everyone. So today we will talk about the week 8 assignment 8 for the course classical mechanics of a single particle, and the course instructor is Professor Supratik Banerjee, and I am the primary NPTEL teaching assistant. So let's start. So basically what we will do today, we will basically do some similar question like in the previous week of in the previous year assignment of week 8. So and there will be some extra question as well, because it is a 2-hour class, so that means we have to take a little bit extra questions. So let's start from today's first question. Okay, so this is a constraint, this is a question that the constraint that a particle is restricted to move inside a narrow vertical tube is. Okay, so let me write here. Just a minute. Okay, so basically what is the question? The constraint that a particle is restricted to move inside a narrow vertical tube. So narrow vertical tube, so it is a vertical tube, or I don't just a minute. Okay, fine. So the constraint that a particle is restricted to move inside a narrow vertical tube is. Okay, so narrow vertical tube you can say like that. Then there will be a which one is the correct constant option for this case. So I have to just a little bit tell about these four type of constant. So what are these constant? First it is holonomic, right? So holonomic constant is in the form of, like, let's say if, and then let's say u1, u2, u3, then t equals to 0. That means the constant which is given in this function, this given in that form, then it will be known as holonomic constant. So what is the u1, u2, u3? Basically u1, u2, u3, these are the generalized coordinates. Okay, and obviously for holonomic case we should have the equality sign, that means the equation like thing, equation and equals to 0, this type of form should be there. So this is the holonomic condition. Okay, fine. Now coming to the another option, which is unilateral. Unilateral means what? Unilateral means like this will be like less than, greater, equals to, greater than, equals to, less than, greater than. This type of sign will be there in the right hand side. Okay, so instead of the equal one. Now coming to the another option is scleronomic. Okay, so what is scleronomic? It is not showing. Just a minute. why that pointer is not showing, I can't understand. Just a minute, please. Okay, fine. Sorry for this interruption, but I could not understand that why the pointer is not showing here. No pointer is showing, but now it is gone. Okay, fine. So what is scleronomic? Scleronomic means it will be, this constant will not, I don't understand where is the cursor right now. It will not explicitly depend on time. Okay, so this will be a scleronomic one. Now coming to the fourth option is a rheonomic one. So rheonomic means will explicitly depends on time. Okay, so these are the four conditions. Now come to the option here. So what is the question? That a particle is restricted to move inside a narrow vertical tube. So if it is a constant to move in a narrow vertical valve, so that means it will be like a motion with the change in space only, not in time, right? So I can say that this motion is scleronomic, not rheonomic. Okay, so as this is a one option, so that means it will be scleronomic. Yes. L-E-R-O, scleronomic. Okay, fine. So how it is coming as scleronomic? Because you can see that if we are talking about the motion inside a narrow tube, that means this, for this case we are not talking about the time explicitly, we are just talking about the change in that space only. So as there is no time dependency in that constant equation of motion, so that means we can say that the equation the constant type is scleronomic. Okay, now coming to the question number 2, the constant that a particle moves only on the surface of a sphere of radius r. Okay, so this is a sphere and the particle is constrained to move only on the surface, that means only on this part. So if I am talking about this one as r, the radius of the sphere is r, so that means the particle should move on the surface, that means on the surface of sphere. So equation of constraint is, let's say, x square plus y square plus z square, which is equals to, let's say, r square in 3D. as it is a sphere. Okay, so we can see that this is the equation of constant in our case, as the particle is a constant to move on a surface of sphere of radius r. So what is this one? What are the options given here? The holonomic and scleronomic, non-holonomic and rheonomic, bilateral and holonomic, unilateral and non-holonomic. Okay, so holonomic and scleronomic, that means it should be equal and then there will be no t. Non-holonomic and rheonomic, that means it should be less than or equal or greater than equal or less than or greater than, and then rheonomic t is there. Bilateral and holonomic. Bilateral and holonomic means it should be equal, and bilateral means again it is equal. Now coming to the unilateral, means like this one or this one, something like that. And non-holonomic means this one is also again this one. Now we are having the expression where x square plus y square plus z square equals to r square. That means we can see that this is nothing but a holonomic one, because I can write it like x square plus y square plus z square minus r square equals to 1. So that means it is a holonomic, and as well as it will be a scleronomic. H no not t dependent. Okay, so holonomic and scleronomic. So I can say that the motion is holonomic and scleronomic. Okay, so this first option is correct one. Okay, fine. Now coming to question number 3. What is question number 3? The constant that a particle is restricted to move on the surface of a cylinder of radius a. Okay, so first of all we need to write the constant of motion for this case. So for this case, the constant that a particle, the constant of motion will be like motion let's say x square plus y square equals to s square. Okay, so this is the equation of constant. So that means f of x y I can write it x square plus y square minus s square, which is 0. So that means you can see that this is holonomic. Okay, so this is holonomic as well as this is scleronomic. How? Because no t dependence explicitly. Okay, so now I can see that x square plus y square equals to s square. That means the particle is restricted to move on a surface of a cylinder of radius a is holonomic and scleronomic. And obviously there will be a non-holonomic and rheonomic is not there, bilateral holonomic is not there, rheonomic is not there. So that means the actual answer will be holonomic and scleronomic. Okay, coming to the first question. First question is, which of the following is not necessarily true for a holonomic constant? Okay, so for holonomic one, as I already mentioned, if u1, u2, u3, u4, t is equals to 0. That means there will be one okay, use generalized coordinates equality, shine, and another one is sorry, may or may not depend on time. Okay. Now coming to the option, it can be expressed as an equation, that is true. It may involve coordinates and time. Yes, it's true. It always involves only generalized coordinate velocities. No, it is not true. It can be unilateral. It cannot be unilateral. Okay, because always it is just equal sign. Okay, so that is also true. That means which one is not correct? Not necessarily true. That means it always involves only generalized velocities, because we can see that the T1, U2, U3, these are the generalized coordinates. So obviously it can be generalized velocities. I don't have any issue on that, but it is not correct that always it will be a generalized velocity. It can be anything like generalized momentum, generalized coordinate like x, y, z, or q, q dot, or something like that, or t can also be the generalized coordinate. So that means which of the following not necessarily true? Not necessarily true means like it can or cannot be the true one. So it always involves only generalized velocities? No, that is not the correct one. So this is the answer for this question. Okay. Yeah. So question number 5. Which of the following is the correct statement regarding the principle of virtual work? Okay. So what is basically the principle of virtual work that we have to do? Okay, so what is the principle of virtual work? So before that I just want to mention that what is virtual work here. Okay, so after that we will talk about the what is the principle of virtual work. Yeah, so let me write here virtual work. So the work of a particle, like of a sorry, yeah, the work of a force on a particle along a virtual displacement is known as virtual work. So it's very simple, that like that virtual work can be defined as F dot delta R, where this is the displacement, but it is virtual displacement. This is a very important one. Okay, so virtual work means the force into the virtual displacement. So this is the virtual displacement. Now coming to the virtual displacement definition. So virtual displacement definition can be written as like so this is a hypothetical infinitesimal change in the system's configuration Okay, so hypothetical and infinitesimal change in the system's configuration that is consistent with the constraints at a given instant but not necessarily the actual motion. It is not an actual motion, that's why it is known as a virtual displacement. So what is virtual displacement? It is the hypothetical and infinitesimal change in the system's configuration that is consistent with the constraints at a given instant but not necessarily the actual motion. So the work done which is coming from that delta r, which is virtual displacement, is known as a virtual work. So this is virtual work. Okay. Now coming to the principle of virtual work. So principle of virtual work told me that, let me write here the statement first. Just a minute. Yeah. Principle of virtual work. Okay, so what is this one? This is like for a system in equilibrium. This is very important. In equilibrium, the total virtual work done by all forces during any virtual displacement consistent with constraints is 0. So that means we can say delta W equals to 0 in equilibrium. So in equilibrium, the total virtual work done by all the forces during any virtual displacement consistent with constraints is 0. So this is the principle of virtual work. Okay. Now coming to the option here. Okay, virtual work. So which of the following is correct statement regarding the principle of virtual work? That means the virtual work is always equal to the real work done. No, virtual work is not equal to the real work, because virtual work means you can see that delta W is equals to F dot delta R. So it is the force into the virtual displacement. Constant force do not do no virtual work. This we will come a little bit later. Now coming to the third one, virtual work is only defined for rigid bodies. No, this is also not correct. Virtual work depends on the choice of generalized coordinates. That is also not correct. Now coming to the second option. The second option told me that whether the constant force is going to do no virtual work, or is it going to do any virtual work. Okay. So the main thing is that constant force is applied at the perpendicular direction of the virtual displacement. Now you can see, if I talk about constant force as Fc, let's say, and Fc is perpendicular to the direction of delta R, That means I can write here delta W equals to Fc dot delta R. So Fc delta R cos theta, and I can say that if it is a 90 degree between that Fc and delta R, then it will be like mod Fc mod delta R cos 90 degree, and cos 90 degree is 0. That means delta W is 0. So what does this means? This means that delta W is equals to 0 for constant force. So as constant force is basically applied at the perpendicular direction of the virtual displacement, that means we can conclude that constant forces do no virtual work. Okay, so this is the conclusion from that question number 5. So we can see that which of the following is the correct statement regarding the principle of virtual work. So first of all, what is virtual work? Virtual work is the work of a force on a particle along virtual displacement is known as virtual work, and the virtual work is F dot delta R, and delta is the virtual displacement. And what is virtual displacement? Basically, this is a very hypothetical and infinitesimal change in the system's configuration that is very much consistent with the constant at a given instant, but not necessarily the actual motion. So delta W can be written as F dot delta R, where delta W is the virtual work. Now coming to the principle of virtual work, principle of virtual work told us that for a system in equilibrium, the total virtual work done by all the forces during any virtual displacement consistent with constants is 0. So that means delta W is equals to 0, total virtual work is equals to 0. Now coming to constant force is doing any virtual work or not. So basically constant force is the direction of the constant force is in such a way that it will be the perpendicular direction of the virtual displacement. So that means we can see that the Fc and delta R has the angle between them as theta, which is 90 degrees. So Fc delta R cos theta cos 90 degree, which gives the 0. So that means for constant force we can have the delta W, which is the virtual work, is 0. So that's why we are writing here constant forces do no virtual work. Okay, so this is the case. Now coming to the question number 6. So which of the following is not true for a holonomic constant? Okay, again the similar question for the holonomic one. So holonomic means it should be F 1 into t equals to 0. This should be the equation, right? So it can be expressed as an equation between coordinates and time. Yes, that is true. It may contain time explicitly. That is also true. It can never be an inequality. That is also true. It is always non-integrable. No, it is not true. Why? Because I can tell that, as I mentioned, u1, u2, u3, t is equals to 0, and that means u are generalized coordinates and t is time. So by giving the proper condition on that f u1 into u3 t equals to 0, I can say that integration of u1 u2 t dt or du is something. So that means it is integrable. Okay, so this is integrable. So this one is, it is always integrable. That is not correct, and they are asking that which of the following is not true. So this one is not true. Okay, so for holonomic case, so far what we got to know that it can be expressed as an equation between coordinate time. It may contain time explicitly, it may not also contain time explicitly, it can never be an equality, it will be always an equality, and then it is always always integrable with given some conditions as well. So this is the one, and another condition was there, we have already explained that for the holonomic case, is that so it is not necessarily always involves the generalized velocities. Obviously generalized coordinates means it can be velocity, acceleration, momentum, anything. So it is not necessarily always be the generalized velocities for the holonomic constants. So that is also the one point we had. Now coming to question number 7. So a particle is constant to move on a surface of a cone with its tip at the origin. A suitable constant is what? Okay, so for that case, I just want to know here the coordinate what we are going to take for a cone. For a cone, we will take r, theta, phi as coordinate basis, right? Yes, so r, theta, phi we will take as coordinate basis. Now we need to know that actually it should be, yes, okay. So what is r and what is theta and what is phi in this case? So that we need to know here. So basically here I can write one thing that yes, r is what? R is the distance from the origin. What is theta here? Theta is polar angle, basically angle from z axis. And what is phi here? Phi is the azimuthal angle. What is this? Like angle in the xy plane from the x-axis. Okay, so these are r, theta and phi. Now coming to the g, what they are telling, they are telling that the equation of the cone will be a particle constraint to move on the surface of the cone with its tip at the origin. So for this condition we can say that like the cone and on the surface means all the points have same angle theta from z-axis, right? So that means we can definitely say that theta is constant here. Okay, so when the particle constraint to move on the surface, we will have the conclusion that theta is going to constant. So now let me go for the options. You can see that r equals to r. So r equals to r means this is nothing but a sphere equation that we will talk a little bit later also. It is not a cone, it is a sphere. Now phi equals to constant. Phi equals to constant is like it is a plane or half plane in 3D, not again a cone. Now theta equals to constant, as we already mentioned. This is a cone and the motion represents that the particle is moving on the surface. And now one can tell that if theta equals to constant, then sin theta will also be constant. Yes, that is true, but it is not convenient and direct, I can say. It is not convenient as direct expression. So that means theta equals to constant, that is the correct one for this question. So when we are talking about the particle which is constant to move on a surface of a cone with its tip at the origin, the suitable constant will be theta equals to constant. Okay, yeah. Okay, fine. Now the particle moves on a plane inclined at an angle alpha with the horizontal, taking xy as coordinates. The correct holonomic constant is. So this is like this one. This is alpha. Now they are telling that it is y and it is x. Now we can say from tan alpha simply y divided by x. So I can say that y equals to x tan alpha. So this is nothing but the equation of the constant. So you can see the option here, y equals to x tan alpha. This is the correct one. X square plus y square equals to r square. This can be like the equation of that circle. Then this one is also not correct, and y equals to constant is also not correct. So the correct option will be y equals to x tan alpha. And how did we do that? Do that. The particle moves on a plane. It is tailing and inclined at an angle alpha with the horizontal. So this is the plane, I can say, which is inclined at the horizontal or with the horizon with the angle alpha. Okay. Now from this figure I can definitely tell that what is tan alpha. Tan alpha will be y divided by x. So that means y equals to x tan alpha. So the first one will be the correct option. Okay. Now coming to the question number 9. So which of the following represents a valid constant for a particle moving on a spherical surface of radius r in r theta phi coordinate? Okay, so for this case, as we have already mentioned that as this is given like the spherical sphere, like spherical surface, so that means we have to take the basis as r theta phi. Okay, so r theta phi, and what are r theta and phi, that we know. Like let's say I am having a sphere with radius r, and let's say I am having a point which is r theta phi, but as they are telling that this will be a valid constant for a particle on the spherical surface. On the spherical surface means the particle should be here, somewhere on the surface. So that means if for each and every case our r, which is the distance of that particle from the origin, it should be equals to r. That is the constant equation. Right? because they are telling that the particle should be on the surface of the sphere, and the sphere has the radius r and capital R, so we can say that the smaller is nothing but, I can write here what is smaller is distance of the particle from origin, and obviously as on the surface they are talking, that means from origin it is always r smaller, which is equal to capital R. So that's why it is will be the correct option. Okay. Now we can move on to the next question. Which of the following is not a constant force? Right? Okay. So which is basically constant force and which is not the constant force? This we can tell. Okay. Right here, which is constant force. What is the definition of constant force basically, right? So the force which arises due to the restriction imposed on the motion of a particle of particle or body. Okay. So constant force is the force which basically arises when we are going to put some restriction on the motion of the particle. Okay. So now come to the options here. So normal reaction force, let me write here basically. Normal reaction force. What is this one? This is nothing but the reaction due to contact. Like we are going to change the, we are going to do something, we have restricted the motion of the body, motion of the particle, so that's why they are just giving us the back as normal reaction force. So obviously it is a constant force. Now coming to the second option, the tension in a turn string of fixed length. So the tension, this is also a force which is geometric constant. So this is also a constant force. Now coming to the third option. Third option is gravitational force. So we can understand that the gravitational force is no longer a constant force, because gravitational force is applicable for all the particles whenever whether or not it is going to on a motion. Okay. So gravitational force is applicable for every particle, and we are not going to put that manner, or it is not going to produce at the time of that imposition of some restriction on that body. So gravitational force is not a constant force. Now coming to the force of contact between a particle and the fixed circular ring. So this is also a contact force. So that is also a constant force. So we can see that the actual option for this case will be gravitational force. This is not a constant force. Okay, now come to the next question. A particle of mass m is constant to move on a surface defined by x square plus y square equals to s square. Using the Lagrange's equation of the first kind, the equation of motion is what? Okay. So equation of constant is given. X square plus y square equals to a square. Now I can write it like the constant function f, which is a function of x and y, is equals to x square plus y square minus a square, which is 0, right? I can write it like that. So now coming to the okay, and I can see that x square plus y square minus a square equals to 0. Which type of constant it is? It is holonomic and scleronomic as well, because no t part, and this is an equation. Okay, so we can see that this is the equation for the holonomic and scleronomic constant. Okay, now coming to the Lagrangian equation of the first kind. So what is this one? This one is nothing but m r double dot equals to f plus lambda grad f. So what are these terms? Let me write here. M r double dot is inertial force, F is applied force, and lambda is Lagrange multiplier that basically account for the constraint force. Okay, and that F is the constraint function. So for this case we can write that m r double dot equals to f plus lambda grad f, and in our case right now f equals to 0, because you can see that in that question a particle of mass is constant to move on a surface, but defined by this using Lagrange equation of first kind, the equation of motion is 1. So here they didn't tell about the applied force at all, so that means we can say that the applied force equals to 0 for this case. So I can just simply write here m r double dot equals to lambda grad f, and what is f here? F is equals to x square plus y square minus a square. So we can calculate grad of f. So grad of f is equals to grad of x square plus y square minus a square. So like 2x I cap plus 2y j cap. But you can see here that in the option they are not talking about that gradient result. So we can simply tell that this is the correct option. M r double dot plus lambda grad of x square plus y square minus a square equals to 0. Yeah, actually okay. So it should be just a minute. It should be like this one. Sorry, it should be this one. It is plus f plus equals to 0. Okay, so from this case I can see that as f equals to 0, then I can say this equation will be in this form. Just a minute. Yes, it will be in the form of m r double dot plus f plus lambda grad f equals to 0, and as f equals to 0 I can say that m r double dot plus lambda grad f equals to 0. So this will give me the equation as m r double dot plus lambda then grad of x square plus y square minus s square equals to 0. So that means we can come to the option number 1 here. Okay, so now we can come for the next question. Which of the following forces is not a constant force? Again, it is very similar to the previous question. That normal reaction from a surface, it is a constant force. Tension is again a constant force. Gravitational is not constant, but centripetal is also a constant force. Okay, so from these things we can conclude gravity is not a constant force. Okay, so maybe I can take this one, this. Okay, fine. Now we can go for the next question. A constant force always acts along the displacement vector, perpendicular to the displacement vector, acts perpendicular to the virtual displacement, never acts in real numbers principle. Okay, so for the constant force case, we know that it do no virtual work. That means delta W equals to delta dot F is equals to 0 for constant force. That means for constant force is perpendicular to virtual displacement. Okay, so we can see that our force is always, constant force is always acts perpendicular to the virtual displacement. So this is the answer. Okay, now we can come for the next question, equation number 14. If phi is a cyclic coordinate in the Lagrangian of a particle, then which one will be the conserved quantity? Okay, fine. So it is saying that phi is cyclic coordinate. So what is the meaning of the cyclic coordinate? Cyclic coordinate means it will be like del L del phi is equals to 0. This is the condition for the cyclic coordinate. Now to know that what is the conserved quantity here, we can tell the equation of the Euler equation basically. Okay, so the Euler equation is here, ddt of del L del phi dot minus del L phi equals to 0, right? Now we know as phi is cyclic, del L del phi equals to 0. So ddt of del L del phi dot is equals to 0, right? So I can see that from this equation del L del phi dot equals to constant, and del L del phi dot is nothing but my p phi. Okay, p phi is constant. And what is p phi? P phi is angular momentum about z-axis, where r, theta, phi we are taking. So we can say that our p phi is constant as del L del phi equals to 0. So angular momentum is conjunct. Okay. So angular momentum about the z axis is conjunct here. Okay. Yeah. So as the phi is a cyclic coordinate, so that means I can tell that the angular momentum about the z axis is conjunct here. Okay. Now coming to 15. A constant force always does positive work, always acts along the displacement, always acts perpendicular to the virtual displacement, does not appear in generalized coordinates. So obviously we told that this one is the correct one. Why? Because the constant force is the one always perpendicular to virtual displacement. So this is the correct option. Okay. Yeah. Now coming for the question number 16. The primary purpose of the principle of virtual work is to conserve energy, to simplify Newton's law, to eliminate the constant forces from the equation of motion, or to find the real work done by applied forces. So from these options we can say that the correct option will be the to eliminate constraint forces from the equation of motion. How? That is the main goal, right? So we told that principle of virtual work tells us that delta W equals to 0, where delta W is the total virtual work done by all the applied forces and with the virtual displacement. So for the constant force, we know that they are not doing any work. So that means if I take care about the virtual forces in our calculation, the virtual work in our calculation, then we can safely neglect the constant forces, because constant forces does not do any virtual work. So the principle simplifies the equations by avoiding the explicit inclusion of constraint forces. force. Actually, the constant force are very much problematic for our calculation because we don't know the behavior of these constant forces that much. So to eliminate the constant forces, we have to include the principle of virtual work. If I include the principle of virtual work, then we can safely ignore or eliminate constant forces from the equations of motion. That is the main goal for the principle of work inclusion. Okay. Now coming to the question number 17, here also they are asking that the main goal of the principle of virtual work is. Okay. So again, the main goal is to eliminate the constant forces from the equations of motion. So the main goal of principle of virtual work is it accounts for constraints geometrically without solving for the constraint forces. That is the main aim, because we don't want to talk about the constant forces, or we don't want to take care about the constant forces in our equation of motion. So that's why we just introduces the principle of virtual work. So the main goal of the principle of virtual work is that it accounts for the constants geometrically without solving for the constant forces. So the correct option will be to account for the effect of constants without explicitly including constant forces. That is the correct option. Okay, now maybe we can come for the next question. Yeah, a particle slides on an inclined plane at angle theta with the base at x equals to 0. If L is the length of the plane, then the constant equation of constant is what? Okay. So for this question, maybe I can draw. Yes. So this is theta, and this is x equals to 0. They are telling. Now the plane is constant to move on the on this plane, right? The particle is constant to move in that plane. And what is L? L is the length of that plane. So I can safely tell, let's say this is Z, so we can see that Z square plus x square equals to L square. This is simply a hypotenuse rule, Pythagoras rule, right? Another thing we can do, that tan theta is nothing but Z divided by x. So Z can be written as h tan theta. Okay? So these two are the equation of the constants. One is coming from the L perspective and another one is coming from theta perspective. So now can come for the option. A particle slides on an inclined plane at an angle theta with the base at x equals to 0. If L is the length of the particle, the constant is. Okay, the answer is Z equals to x tan theta and x square plus z square equals to L square, these two. So that means you can see that 2 and 3 both are correct. Okay, so for question number 18, we can see z square plus x square equals to x square and z equals to x tan theta, both are the equation of the constants. Okay. Now coming to the equation number 19. Okay. So what is question number 19? A particle moves on an inclined plane of angle alpha with respect to the horizontal The correct holonomic constant is, they are asking that holonomic constant. Okay, that means they are asking that equation of the constant here. So this one again is the case where it is alpha. Let's say the particle's motion is constant to the plane. The plane can be expressed as a linear equation relating the coordinates, right? In the general plane in 3D space, I can write a general plane equation in 3D is ax plus by plus cz equals to d, because a, b, c and d, x, y, z are the coordinates, right? So where that a, b, c, these are the normal vectors and d is a constant. Okay, now for the inclined plane, at angle alpha, we can say a, b, c is nothing but cos alpha 0 sin alpha. Why? Because you can see that we are talking about ax plus by plus cz. So it is like cos alpha is according to a, which is x cos alpha, then x sin alpha, z sin alpha, and then for b it is 0, because it is at x and z. So I can write here that x, okay, so it was previously ax plus by plus cz equals to t. Now in this case, x cos alpha plus 0 into y plus sin alpha into z equals to h. So this will be x cos alpha plus z sin alpha is equals to h. So this will be the case, right? So now we can see the option x cos alpha plus z sin alpha equals to h. Now coming to this one is a plane passing through the origin which is of tan alpha, but it does not include an offset or a general position. It is like when, okay, so for this case we can say that this is like when it is a the plane is passing through the origin, but in that question they are not telling that the x equals to 0 or something. So that means we can say that it is true when the plane passes through origin. Okay, this is not correct because this is a circle with the constant one. Like this represents a cylinder, not a plane, and this is the correct one. And z is equals to constant is a horizontal plane, that is also not correct. So I can tell this other options as well. Z equals to x tan alpha. This represents the plane which passes through the origin with slope tan alpha, right? Now coming to x square plus y square equals to constant. So for this case, this represents a cylinder, not plane. Now x cos alpha plus y sin alpha, z sin alpha equals to h. This is the correct. Now another one is z equals to constant. So again, this is horizontal plane, but in our case it is not a horizontal plane in our question. with the slope is there, so that means it equals to constant, not the correct one. So that means in general form x cos alpha plus x sin alpha equals to h is the correct option. Okay. Now coming to the next question. 20. The Lagrangian equation of the first kind for a particle moving on a surface of a sphere. Ignore gravity with radius a. Okay. So first of all we have to write the equation of constraint for the particle moving on the surface with radius a. So this is what? This is x square plus y square plus z square equals to a square. So f of x, y, z is nothing but x square plus y square plus z square minus a square. Now coming to the Lagrange's equation, so it is m r double dot plus lambda delta f equals to 0 as f is equals to 0, which is the applied force. So in our case there is no applied forces, right? So that means the Lagrangian equation of the first kind for a particle moving on the surface of a sphere ignoring gravity, right, with radius a is how much? So we can see that m r double dot plus lambda grad of x square plus y square plus z square minus a square equals to 0. Now I can also see that r is x square, y square, z square root. So r square will be x square plus y square plus z square. So we can definitely write it like m r double dot plus lambda grad of r square minus a square equals to 0. Now come to the option here. Okay, see the first option. In the first option it is showing that similar but not exactly correct, because you can see that there is x double dot, not r double dot, and here also it is not correct. The third one is also not correct. Now this one is correct. Why? m r double dot plus lambda grad r square minus a square equals to 0. Okay. So this is the case. Now we can see that this one is correct option. Okay. Now coming to the next question. Question number 21. A particle is constant to move on a sphere of radius r in the absence of external forces. Using Lagrange's equation of first kind, the motion satisfies which expression? Okay. So for this case also we can see that, so the constant, equation of constant is r equals to r, right? Okay. Now, so constant function f of r is equals to r minus capital R, which is 0. Now coming to here, m r double dot plus lambda grad f equals to 0. So m r double dot plus lambda gradient of r minus r equals to 0. Or I can see basically here, see r is equals to r, that means r square will be equals to r square. It should be like that. It is not the correct one, because we can see that r square is equal to x square plus y square plus z square. That should be r square, right? That is the sphere equation. Yeah, I should not write like that. Okay, let me just remove this one. as this is a sphere. In that question they are saying that it is a sphere. So sphere means the equation of constant will be like x square plus y square plus z square equals to r square, and this whole is nothing but r square equals to r square. So f of r is like r square minus r square equals to 0. Now coming to the Lagrange's first kind of equation of first kind, right? Equation of first kind. So that is m r double dot plus lambda grad of f r is equals to 0. So I can say here m r double dot plus lambda gradient of r square minus r square equals to 0. Now gradient of r square minus r square is 2r. Actually it should be in the vector form. So the answer is amr double dot plus lambda 2r is equals to 0. So amr double dot plus 2 lambda r vector is equals to 0. Now, okay, maybe we can go for the option first. Yes. So what we got amr double dot plus 2 lambda r equals to 0. Now you can see that the lambda is a constant one. So 2 is also a constant. So 2 lambda is also a constant. So I can just replace that one by another lambda prime or something. So that is the expression. So coming to the option here, actually this is the correct option. Amr double dot plus lambda gradient of r square minus r square. But here it will be the r square one. But if the vector condition is there, that means if it is a lambda prime, then that will be a correct option. This is not the correct, this is also the correct. So option 1 or option 3 is correct, but option 1, if r is r vector, and for this case, if lambda is 2 lambda. So these two conditions should be satisfied, then only equation 1 and equation 3 both will be the same one, and both will be the correct option. Okay. Now coming to the question number 22. For the same particle constrained to the sphere, which of the following is a valid constant equation? So constant equation means like same particle constant means at the very previous question what we were discussing. So the particle moves on a surface of the sphere. So for this case, I can see x square plus y square plus z square equals to r square. That means I can also see that r square equals to r square, which is constant, and r is constant. So the constant equation is r equals to constant. This is the equation, valid constant equation, r equals to constant. Theta equals to constant is for that cone question what we talked, and phi equals to is constant is also not correct. Square sin square theta equals to constant, that is also not correct. Okay. Now we can go for the next question. For a particle constraint to move on a cone of semi-vertical angle beta, right? which of the following remains constant? So that is also a Euler-Lagrangian equation question, and after that we can talk, right? So okay, for a let me write here. For a particle constrained to move on a cone of semi-vertical angle beta, for this case it basically satisfies R cot beta. I mean, like, it can be written as, so which is tan beta equals to R divided by Z. So R will be Z tan beta. Okay, so why it is like that? Because the particle moves along the cone's surface, and as there is rotational symmetry around the axis of the cone, we can see that the angular momentum about that axis is conserved. Okay, so for this case we can say the angular momentum is conserved. Now what is the expression for the angular momentum in this case? The angular momentum expression will be Lz, which is m r square, let's say effective I can say, and phi dot. And what is r effective? R effective is distance from the axis of rotation. So for the cone, the effective radius can be written as r cos beta. So then I can say here that our Lz, which is m r effective square phi dot, is nothing but m r square cos square beta phi dot. Okay, this is constant, this is conserved. So if it is conserved, so I can write here it is conserved. So particularly it can also be written as that r cos beta phi dot is conserved. So maybe we can go for this r cos theta cos beta phi dot. So this is constant. So for this question what we did, we just calculated that for a particle constant to move on a cone of semi-vertical angle beta, we have that r equals to z tan beta. So I can write here that z equals to r cot beta. And for that particle moves along the cone's surface, there is rotational symmetry around the axis of the cone. Angular momentum over the axis is constant. So the angular momentum is of m r square phi dot. So r is the distance from the axis of rotation. So r will be r cos beta. Then Lz is like r cos beta phi dot. This is a conserved quantity for this case. Okay. Okay. Now coming to the 24th question. A particle moves on the inner surface of a cone under gravity. The cone has radius r equals to az and semi-vertical angle theta. The Lagrange equation using constraint this one is, okay. What is the constant given here? Phi xz equals to x square minus z square, x square theta equals to 0. Okay. The constant xz is x square minus z square, x square theta equals to 0. This is, let's say, fxz. Okay. So the equation of motion by Lagrange's first kind of equation is m double dot plus f plus lambda grad f equals to 0. Now what is f here? It is applied force. So now in this case, as they are talking about the gravity in this question as well, then I can tell that it is minus mj cap, because it is applying in the negative direction. You can see here, because these are minus g are given, so that means we have to take care about the applied force as the gravitational one as well. So now m r double dot minus mg z cap plus lambda grad of what is that one? X square minus z square, x square theta. So if this is the case, which is equals to 0. So now m r double dot minus mg z cap plus lambda grad phi is equals to 0, where phi is x square minus z square, x square theta, which is equals to 0. Now we can see the option here. Yeah. So yes. This is m r double dot minus mg plus lambda grad phi equals to 0, where phi is x square minus z square, x square theta. So this one is the correct option, and they did not write here all the explicit function of that z. If I want to write here, that is also fine, but as the first option is already mentioned the exactly same expression, then we can see that this one is the correct option. M r double dot minus mg plus lambda delta grad of phi equals to 0. Okay, now coming to here, which is the last of question. The particle of mass m moves on the surface of an inverted cone defined by z equals to r cot theta under gravity. The Lagrange's equation of first kind is, okay, under gravity they are mentioning here. So we have to take care about the gravity in this case as the applied force. The equation of constraint is what? Z equals to r cot alpha. So we can say that the z minus r cot alpha equals to 0. So from Lagrange's first kind, we can have m r double dot plus f plus lambda grad f equals to 0, where our f is right now as z minus r cot alpha. So we can see m r double dot plus f plus lambda grad of z minus r cot alpha equals to 0, and here F is minus mg z cap because it is under gravity. Let me write here properly. Under gravity. So this will be m r double dot minus mg plus lambda grad of z minus r cot alpha equals to 0. So maybe we can see the option. Yes, this one is the option. Okay. So I think these are the things. So let's see it again. This lambda grad of z minus r cot alpha equals to 0. Okay, so maybe I can go through from the very beginning a little bit so that it would be understandable by all of you. So maybe I can go from the first. So as it was not said properly, so this one is the first question where we are having that holonomic one. Actually not holonomic, we have to explicitly tell. If we are going to tell explicitly, then that will be a scleronomic one because it does not depend on time. Okay, so the 3 option is correct. Now coming to the next question. Okay, this one is 1. Because the constant that a particle moves only on the surface of a sphere of radius r is x square plus y square plus z square equals to r square, and this does not depend on time, and this is a equational motion, and the equation function is like x square plus y square plus z square minus r square equals to 0. Okay, now coming to the third question. The constant that particle is restricted to move on the surface of a cylinder of radius r, that is also 1.